Good evening to all the students. Welcome to week 9 discussion of the Electrical Machines 2 course. So last week we discussed some important concepts on the starting of induction machine and some derivations of the voltage ratios and all. So today we will be discussing about another important topic related to the machines. So for any motor, three things are basic and also very important. They are starting, speed control, and braking. Let me just write those three concepts here. Right. So till we start the motor, starting is important. And while it is running, we need to control the speed at which the motor is running. That's also another important concept. Finally, we need to stop the motor and we need to also control, like we need to have a hold on the braking of the motor. Now, last week we discussed about the starting methods. Why do we need a starting methods and what's the purpose of it and how can we achieve a good starting because there are some problems associated with starting the machine. So we discussed those. Now, this week we will be discussing about the speed control of the induction machine. So when coming to the speed control, let's actually look how a speed curve looks like for the induction machine. So for the past 2 weeks, we were discussing some torque speed curves of a induction machine, if you remember. So let me just draw it one here. So the x-axis is slip we used to draw, if you remember, and y-axis is torque. And here from in the x-axis from left to right the slip will be increasing. So here the slip is 0 and here the slip is equals to 1, and let's say this is the maximum torque line. We were starting from slip is equals to 0 and slowly slip increases and maximum, and left this is the starting torque. T is starting torque. Okay, now this is what we know, and we know torque slip curve. Now if you want to convert it to a torque speed curve, we know at the s is equals to 0 you will have a what is the speed? It is ns, because s is equals to 0, s is equals to ns minus n r by ns, and this is ns. So ns is here in 2f by p, that is rps, rotations per second. Now as we move from left to right, you will see an increase in the slip, so there will be a decrease in the speed of the rotor. So as decreases from when s is equals to 1, what is nr? Nr will be 0. This is 0 here. So if you see from left to right slip increases, from right to left speed will increase. So we are now interested about the torque speed curve. So let's just reverse this curve and then we will start discussing our concept of torque speed. The only purpose we are reversing it because we need to have a good torque speed discussion. So let's draw it from increasing trend. I'm now drawing it in a this is torque and this is speed here. So here it will be, if we increase from here, it's just the speed is now here 0 and here it will be ns. From here to here speed is increasing. Now starting point, this is where the speed is 0, it will go, and let's mark maximum torque already here, and it starts from here. If you see this curve at 0 speed we have a starting torque, right? So if this is starting torque, start from here, it will reach maximum and then it will reach zero at where ns is speed is equals to ns and slip is equals to zero, and this is the point. Now this is how a torque speed curve would look like. And now if you mark the maximum torque, we know we are calling it as an alpha. Alpha is the slip at which T max occurs. Slip at T max. Okay. Usually in the theory we studied that it occurs around 10% of the float slip, like that. Anything could be, but usually they call it like that. Okay. There is no rule that it should always be 10% of the float slip. It usually occurs at that place. Now, if we have a motor having torque, slip, and also torque speed characteristics like this, now say we have a load requirement. This is the motor curve. So for whatever load you are using the motor, this is going to give this kind of characteristics only. So this is how the motor would behave for this particular speed. This is the torque it will give. So at initially it will give that much starting torque, and as we progress the speed, as the motor picks up the speed, that is a torque profile it would give. Now we are using this motor to drive a load. Now the load has different load requirement. That curve would be different. Maybe I need constant torque requirement load. Now it will have a constant torque. So our motor should be able to provide that particular torque. Let me just draw. Okay, let's take a constant load requirement. Maybe it is having like this. So this is TL load. Okay, now this particular straight line is the actual um, characteristics of my load. That is a load requirement. That is a load I need to provide from my motor. Now say we have this particular load, full load. Let's say this is the full load torque. This is what I have required, TL. And maybe example, if it is full load, wherever this point is intersecting, that means this particular full load torque and my motor torque can be provided if I operate my motor here, right? If I able to operate my motor at that particular speed, it will provide that particular torque which can be fed to the load. So that is my load requirement. Maybe full load slip. This is SFL, full load slip, maybe around 5% usually. They say that's not a rule, but usually they say it's a 5%. Let's assume that's around full load slip is 5%. Now, as we know, our torque maximum is around 10% or something like that. Now, if we want to supply this particular full load, not if, like I want to supply, because this is speed control, right? Now I want to supply this particular TFL, that is full load torque, at different speeds. Let me just write here the concept which we are discussing. Okay, now I want to supply this particular load torque at different speeds. So from this figure which we are seeing, we can see the speed at full load torque is almost close to ns. So say this one is this particular speed SFL, this is SFL and this is alpha, and this particular speed, let's say this full load speed NFL is almost close to synchronous speed, right? Now can we supply this full load torque at half of this speed, maybe half of synchronous speed? This is ns, this is almost close to ns. Let's say maybe this is ns by 2. I want my motor to supply this particular torque at this particular speed. Maybe curve, I need to change my curve like this or something like this. Anything? Is that possible? Can I change my speed torque curve of my motor? Can I? Anybody? The answer is yes. We can supply that particular torque at any speed you require, maybe half of ns, maybe and some other speed, some x speed you want, we can do that. But we need to do some modifications to our motor in order to supply different in order to supply that particular motor at different speeds. So if you remember 2 weeks back discussion, we discussed that for a slip ring induction motor, as we vary this rotor resistance like R2, R2 plus external R, we were keep on adding these external resistances, right? Yeah. So this adding this external resistances actually improved. If you remember, uh, it changed our torque slip characteristics. So we discussed for a slip ring induction machine how the starting torque is getting improved while we are changing the rotor external resistance. And yeah, now uh, this is also close to some speed control. Like see how we are getting a different uh, speed torque relation, but actually changing the rotor external resistance. If you see this one, if you remember the TE max formula, it is not dependent on the R2. So like, let me draw, it will be clear for you then. So this is TE and this is let's say this is P, and yes, this is something I have. Okay, this is for a R2, for a motor of rotor resistance R2. Now what I did, I added a external resistance. Now my total rotor resistance is R2 plus R external. Now when I'm increasing it, the rotor resistance, I saw an increase in the starting torque. Okay, this is what we observed. But the maximum torque would remain same. That's what we saw from the formula. It's not dependent on the R2. Now I will further increase the rotor resistance. This is how it will come. So as you keep on increasing, so this is for R2, this is for R2 plus R external, this is plus R2 plus twice R external. You keep on adding, you can get an improvement in the starting torque 1, starting torque 2, starting torque 3, varying the starting torque. Now we can see different speed torques. Now if you see, this is my load curve, this is my TFL. At three different instances of curves, I am having three different speeds, of course. So this is three different speeds, NR1, NR2, NR3. Now we can see a very smooth variation that we have achieved now. We just varied the rotor resistance, and at different speeds, now my motor is running and it is able to provide this load torque. Now the question is, can I keep on doing it like now I understood the concept. So if I can vary the rotor resistances in the circuit, I can get different speeds, and that speed can be able to deliver the load requirement. Is it okay to do this? Is there any problem with the um, uh, method we are following here? Everything is good, right? Starting torque is improving, and it is able to have a good smooth variation in the speed. Slip ring induction motor means we can easily add resistances. What's the problem with the circuit? There is only one problem. That is huge copper losses will be there because we are keep on increasing the huge copper loss. So in turn, losses will be there, your efficiency will be reduced. Right? Because we can't just keep on adding resistances to the circuit. Although we are achieving a smooth speed control, it is not at all used. So because of its own disadvantages. Now another method is let's control the maximum let's control the supply voltage itself, right? Supply voltage control also we discussed last before 2 weeks. So if we able to change the input supply voltage, your torque maximum torque would go down. That we have I'll just draw it. Let's draw for like let's say we have for a V supply first supply voltage. Let's say some starting torque. This is for V1. Now we have seen that if you have the supply voltage, yours because if you remember the complete expression, now T is equals to T max 3 by some constant 2 pi rs, and this is V1 square by R1 plus x2 whole square, something like that. It's independent of R2 but dependent on square of the input voltage. Now if you half the supply voltage by half, your torque will be reduced by voltage is half by V1 by 2, your max will be reduced by T max by 4. Huge reduction. Now let's say this is the torque and this is the speed and this is your starting torque and this is T max. Now I have gone for V1 V by 2. Now my torque would go even further down. See, like this. You can see. See the alpha, the slip at which this is the slip at which the maximum torque is occurring. Alpha is equals to R2 dash by X2. Like if you neglect the stator and all, it's a simplified version. This is not dependent on the input voltage. Even if you change V1, V1 by 2, anything, your alpha is not going to change. So that's what we are seeing. Alpha is remain changing for the both curves, but the T max is what it's changing. Now even this is for V1 by 2. Now even I reduce further, even goes down. So let's see, this is your load torque FL. It is giving a variation here, but you see this is very close variation. So you are getting speeds very close to each other. It's not much of a speed control. Like it's providing different speeds, but the speeds are very close to each other. Yeah, alpha remains same. Now there are two disadvantages for this kind of speed control of reducing the voltage. Can anyone say that? One one disadvantage is which we I just discussed. That is very limited range of control. So this is very minute variation you are getting. It's not much when you compare to the this particular thing. So even if you have this kind of maybe you can get different speeds in the if you get that, maybe like this, you can like this, so you can get a good variation in the speed. But in the voltage control, it's just peak is going down and down and down. You are not getting much variation here. You don't get much variation in this speed control. Now, first disadvantage, very limited range that you can achieve the speed control. Second one, if your load torque is constant here, and if we further reduce the voltage supply, so let's say this is V1 by 2, this is V1 by 4, and this is my load torque here, right here, and I'm reducing it further, maybe it will go down like this. With my speed curve, torque speed curve of my motor is such that it cannot even reach the load requirement, right? If we if we further reduce our voltage supply, that's it. Your machine comes to stop because your machine can never provide to a load and it can't meet your load requirement. So the next one is further reduction in supply, machine would stop. Okay. Yeah, this one. Now, if your load torque is not constant, okay. Now, if this method, uh, we are seeing some straight load torque, a very constant load torque. If load torque is not constant, if it's like this method may sustain because torque demands at lower voltage supplies are lesser here. See, if it is not straight line, maybe if it is like that or like this, maybe it will see now it is applying it. If it's not a straight line, the cases might be different. But I'm saying if it's a constant low torque, this further reduction machine would stop. This one if TL is constant. Yeah. Now these are earlier methods we have discussed, adding external rotor resistance to the circuit and also reduction of the voltage supply we have discussed. But these are we have discussed, but not in the context of a speed control. The reason why we inserted rotor resistance is to just keep the maximum torque constant but improve the starting torque. And the reason why we have went further is the voltage supply voltage reduction is even though my maximum torque is going very down, your maximum like slip at which the maximum torque occurs would remain same. We just discussed the concept, but application wise we need a good speed control objective. Yeah. Now let's discuss what is the solution for it. Now the before one, which is having the resistance control, we have seen this is the disadvantage, huge copper losses and efficiency goes down. And when we have a voltage controlled speed control, even though we are getting a very limited range of control, but it's not at all suggestible because it might not make the machine even move. So these are earlier methods we have discussed. Now all these techniques, because they are requiring extra setups, external resistances, making the rotor bars of a motor like accessible like that. But we are still getting a limited speed control only. Like it's not much good even if we do all those and all. We just saw we are getting a very minute area. So what if we could get the entire curve's torque speed curve? I mean, control, speed control. Is that possible? Anyone? Is that possible really? Like, can we just try it? Okay. But what I want to say is, see, the controlling speed by by normal induction machine has different problems. So now that's why people use this DC motors in the speed control. They're very straightforward, and supply is fixed. In DC motor, we see there is no concept of frequency. Now we control the armature voltage, and we also control the field current, and we get smooth control of speed below and above rated speeds. I don't know how much you remember it, because this is the concept of DC machines, electrical machines, one course, but it's very important topics. Now, this compared to these problems which you have just saw in induction machine, it has a in the first case, which we are inserting the resistance to the external circuit, it is experiencing the high losses. It is efficiency is going down. Now, when we are reducing the input supply altogether, we have seen we are achieving a very limited range, and also the machine might stop if we even further reduce the voltage. Now, to avoid these problems, because of these problems, people are going for a DC motor kind of speed control. A DC motor, still we can get a very fine control of armature like speed control. There are two methods: the armature voltage control method and also field current control method, and we get smooth control of speed both below and also above the rated speeds. So, but what is the issue? Here, induction machine, we have a fixed frequency, right? And if you fix the frequency ns, that is 2f by p, that is also fixed, and rotor speed will be very close to ns at full load speed, because at full load your full load slip will be around what, 5% or 6%. Now when full load is 5%, it will be always be close to this range, and this is a slip, uh, it will be always close to some synchronous speed ns now in a steady state. So induction machines were usually considered to be always like uh, more or less rotating at a constant speed around the full load. But previously, there used to be a common question like in traction system, that's trains and all traction system, the motor which is commonly used. Anyone can guess it? What is the most common motor that is used in the traction systems? This is usually very important interview question. Usually people ask like what is a kind of motor they use in the traction. So the answer is DC series motor. Nowadays also it is used, but people aren't talking about whether speed can be controlled at ease with induction motor or not. So if it can be able to easily control by induction machine, we don't even go for DC series motor. It has its own disadvantages. Now, if if we can able to achieve a smooth control in the induction machine speed control, then it's easy. We should replace it. Now, let's say for a given machine, we have a given machine, and our ns is constant, and ns 2f by p, because of supply frequency is constant, the poles is constant when the um, machine is designed. Your rotor speed will also be related to f by p, because if ns is equals to f by p, based on the slip, your rotor speed will also be decided. Now, there came the advent of new technology in the electrical field. Then at that time is power electronic converters. So using power electronic converters, we can able to achieve this speed control very easily. See, what we need to control the frequency, right? let's say ns is to f by p, and r is something speed we have. Now to control the speed, if you want to control nr, ns should be controlled. To control ns, we need to control these three. But out of these three, poles cannot change, two cannot change, it's constant. Frequency also cannot change as of now. We don't know how to change the frequency. But with the advent of power electronics, this problem can be overcome. Can anyone guess how can we achieve this variable frequency using power electronic converters? Any idea? Okay. So we can clearly see by this expression of nr is equals to f by p. Now, if we can control frequency, now if we can able to control the frequency, ns will be controlled, ns will change because f is changing, ns will change, and nr will automatically get affected by the change in the ns. Now, how this can be achieved? Because you can't change f, because f is like a supply frequency, it comes from the grid, 50 hertz here or 60 hertz from another countries, but this particular frequency is the one which we need to control. How can we achieve it? Any idea? Actually, I gave you a hint, like we should be using the power electronics. So we should be using the power electronic converters. I gave you a hint, but can someone tell me how we can incorporate power electronics into the system so that we can get a variable frequency so that I can achieve a good control over the frequency and speed? The goal is to get a armature voltage control and field control similarly as in the DC machine so that they can vary different voltages and frequencies of the machine. Now, see, for a grid, if you take both grid voltage, whatever your supply, three-phase supply, let's say you are generating the supply there and you are utilizing it there at your home, it is fixed voltage you are getting. But that's the beauty of actually power electronic converters. So they can step up and step down the voltage levels by maintaining the power level constant. So can someone tell me how you can incorporate these power electronics converters and systems into our system where we can achieve the speed control? It's simple. Like see, we are having a three-phase AC supply at 50 hertz, a fixed voltage. V and F are constant. Now what I'm expecting, let me just draw on a new slide. Now let's say this is my three-phase supply at 50 hertz. Okay, three-phase supply AC, and there is my output which I will give to my motor. Okay, so there should be something like that. I need to get a voltage control as well as frequency control of this. So if here it is V and F are constant, three-phase supply and frequency are constant. Now at this at this end, I should be able to supply such voltage and frequency which are keep on varying with the load requirement. Now, can we achieve that using power electronics? Any idea? So to achieve that, we are going for a rectifier and also a converter. So I hope you know what all these terms are. Rectifier is something which converts AC signal to a DC signal, and inverter is something which you convert from a DC signal back to a AC. So I already give you another hint. So now can someone tell me how we can merge these two requirements? Okay, let me just draw it here then. So I have a constant voltage and constant frequency, and here voltage is variable and frequency is also variable. Now first convert this AC into DC, because power electronic converters we have DC choppers based converters. Now let's convert this first into a DC. So this is like a AC supply I'm giving it here, and this is the bridge rectifier. I'm getting a DC here, and there should be another level, because this here if you see the voltage is fixed. There is no variation in the voltage. There is the voltage has stepped down or stepped up. That's not happening here. It is just converting my AC to a DC. So the voltage is again fixed, and but I need a voltage variation and also the frequency variation. So what I would do, I would connect simply a, and also of course this is DC, of course this is AC. We would like to have a inverter in between. Okay. So this three-phase inverter, what does inverter do? It will convert DC to AC. Now again I will be left with AC, and my motive is what? To get a variable frequency and also variable voltage. Now how these DC-DC converters work? How can they provide it? That's that's because they have these switches within them. So three-phase inverter would have 6 switches, if I'm not wrong. Now each switch would take some pulses to operate. You know pulses to a switch, right? It's on off, on off, on off. So the way with which you on and off the transistor switch, or the switches, IGBTs, anything, whatever you are using within the inverter, if you can able to control that voltage and frequency of the output signal, it's always very good, because you are able to achieve uh, this concept of having variable voltage as well as frequency, right? Now you need to give pulses to that particular switch inside the um, inverter, such a way that it will always give you a variable voltage and variable frequency. So I'm just marking two control inputs at the bottom of the inverter, where it it can, there will be controls by which we can get a these two controls. One is frequency control, and also this is a voltage uh, voltage control. So these two are the pulses which I am giving to the circuit switches inside the three-phase inverter, such that the output AC what I am getting will be voltage and frequency variable. So these will be these controls which we are raising, by which it will give a balanced three-phase voltage source of variable voltage and also the variable frequency. Now this is directly we will connect. This is like a source to my mother. Now this I'm connecting it. Uh, this is source to my motor there, and this is a three-phase source, and this is induction machine. And now if you see this motor is getting this kind of input from a three-phase inverter, which is having a variable voltage and also the variable frequency. This voltage, this frequency, and this voltage and this frequency, if you compare these two, here we have a constant voltage and constant frequency from the supply, and now we have a variable voltage and variable frequency that we are able to achieve with some power electronics in between the circuit. So now I don't have any problem in achieving the speed control because now with this variable voltage and variable frequency, at any voltage, at any frequency, I can operate and I could get any like at any different speed I can get it, because torque speed curve, if you observe in the previous slide, now this is see the bottom curve, if you see at different torques and speeds, the speeds are different and it is able to supply this particular low torque. So it's not at all a mandatory thing that if you have to supply this particular low torque, your motor should always have to rotate at that particular speed only. That's not a requirement anymore. Since the advent of these power electronic devices, it is easy to get a variable voltage and variable frequency. So if you see this, they will call this as a the three-phase balance, but a variable voltage and variable frequency supply. VVVF they used to call it. Now suppose you have an induction machine, and let's see what happens once we connect this kind of supply. Okay, is it okay? Now we have achieved it. Like okay, we were able to do it, but what's the logic behind it? How does this work for a motor? So can I go for any voltage or any frequency? So that's how we will see here. Now this is what let's say this is stator and rotor. This is we have a machine here. Now this motor have rated speed and also rated frequency, that is 50 hertz, say if it's a rated frequency and it's a rated, it is rotating at a rated speed. Now let's say this rated frequency is 50 hertz and rated speed and also rated voltage. So per phase we already know the formula of rated voltage, right? We discussed this 4.44 k window winding factor. This multiplication of pitch factor and also distribution factor multiplied by flux, frequency, and turns. Now, based on this V rated and also frequency, uh, uh, 5 rated we can calculate, right? This is the 5 rated. So, what is the formula for 5 rated? V rated divided by 4.44 kW F and N1. Okay, now see what are all the constants here. I'm just bringing out the constants. Once you design the machine, 4.44 is constant, that's a term, and kW is constant, that is a winding factor, multiplication of distribution and pitch factor. It's also constant, and the turns are constant. Now, whatever the varying are these V and F. Now, if I write it here, now my rated flux is is proportional to V rated divided by frequency. So this is very very important relation. Now suppose I'm reciting a case here. Suppose my rated voltage is equals to 400 volts and my frequency is 50 hertz. Yeah, this is a rated condition. And I have a 4-pole machine and a rated speed is equals to 120 F by P, 120 into 50 by P, and it will be 1500 RPM, right? This is my case. Now, if I want to run this motor at different speed, I want to run it at different frequency, let's say if 50 hertz, right? Now, let's say I want to run this motor at half of its frequency, that is 25 hertz, because your inverter can give variable frequency now. So I want to run it at different frequency. So if I'm changing this F2, what will happen to my speed? N2 is equals to 120 into 50 by P. This is P 25. This is 750 RPM. So it is 750 here, it is 1500 here. I am trying to run my motor at half of its rated speed. Okay, by keeping my voltage constant. So I'm not varying the rated voltage. Rated voltage is same. In this case also V rated is equals to 400 and frequency is changed and my volts is equals to 4. Now V rated constant. Okay, and rated voltage is constant and your frequency is changed by half and your speed has go down. It's going to below the rated speed. So right, this is 750, which is below rated speed. Now we will also discuss for above rated. So this is for the below rated speed condition. Now, what is the problem? Okay, we have achieved the speed control below the rated speed. Okay, now I'm getting 1500 RPM before and now I'm getting half of it. Okay, well, it's good. I'm getting the speed control. Now, what's the problem here? On the top right corner, I have wrote the formula for phi rated, which is proportional to rated voltage divided by frequency. Now compare that equation with the current modification we have done and tell me what's the problem with the circuit if I do this. See, the frequency has gone down twice, then voltage is constant. Now what's happening? Yeah? So the problem is if you keep the voltage rated constant but you are decreasing the frequency, what is happening to the flux here? What is happening to the flux? It is rising, it is going up. Your rated flux will just go up and up. So my flux is proportional to V rated by F. Now my F is F by 2. I reduced it and my new requirement of rated flux is twice the old one. So your required amount of flux is just gone up. Now whatever it is, motor or transformer, whatever it is, after it is being designed, you will have to look at the BH curve of it. It is very important curve to look at to understand the flux requirement of the machine. So what is the rated flux and what is the current requirement at that particular flux. So let me just draw a sample BH curve This is H. Usually it is proportional to Ni, so it is proportional to current, and this is B, and it is proportional to flux, because flux is equals to B into area, so area is a constant. Once it is in the cone, it is proportional to flux. Now you might have observed like this BH curve, and you will have a not even that settled. So you will have a knee point here, and it settled. Okay. Now this is a knee point here. Okay, this is the knee point, and on top of it you will have maybe your flux is kind of getting saturated there. Okay, after that knee point, your flux begins to saturate. Now, based on this B rated, whatever it is at the knee point, your rated uh, flux density, usually they will design our machine. First, they will look at the BH curve, and they will, after designing the machine, you will know if at this particular rated, this is the amount of current, magnetizing current is proportional to magnetizing current. You will need to provide that's the amount of magnetizing current your machine will draw to provide the rated flux. So in this condition, what happened? I have reduced the frequency by half, and I have saw that there is a twice increment in the rated flux requirement. I kept voltage same. Frequency is halved, and then the level of flux requirement has gone up twice now. So if I look at the BH curve, so previously this is the rated requirement, and this is the B1, and now it is twice. Let's say it is even okay. Maybe here. I'll just maybe here twice. Okay. Meeting this curve maybe here, and previously it is the mini point. Now for the second requirement, this is H, and this is the magnetizing current proportionality. Now see, previously it is IM1 here, less magnetizing current it requires. Now see, for a twice improvement, the amount of flux that is required is twice, but look at the current requirement now. Since the curve structure is like that, even for a smaller increase in the B, the current increase would be much higher. Now my flux density is twice. The current drawn will be very large. So this is the new current requirement, IM2, and motor will get saturated, because when you draw that much of current, your flux, your motor will move to saturation. So how can we avoid this? Very high magnetizing current your machine is drawing. So, but you need a speed control. You have reduced the frequency by half, but that is posing a danger of motor core saturation. So how can this be avoided? So this can be, then people were thinking, how can we reduce the frequency or vary the frequency, but also keeping the rated voltage constant? So flux rated is proportional to V by F. So okay, I will anyhow control the frequency, but I will not control just the frequency if you are going for speeds below rated. Now by reducing the frequency, I have gone speeds below rated. Now to have a good speed control, I won't just control this particular frequency. I will control both voltage and frequency such that my rated flux remains constant. So I want to operate my machine always at this B rated only. So in order to make sure that my flux, which is proportional to V by F, this ratio should be constant. So even if F goes down, okay, I will again reduce the voltage then, so that I can have this ratio same. If I increase this, let's say previously it is 20 by 30. Now, if I am reducing it, like let's say now let's say I have okay, maybe I have gone for 60. Okay, I have to reduce, right? So let's say I have reduced it by 3 times 10. Now again I have to make the ratio 2 by 3 only, 20 by 30. So I will also reduce my voltage by 3 times, 20 by 3. So if you see, again the ratio is 2 by 3. So in that way you have to do some modifications and make sure you are getting a V by F constant. So if I, let's write it here. Now if again I am taking the same condition, before I have 400 volts and 50 hertz. Now if I want to run this motor at 25 hertz, half of its frequency, I need to reduce the voltage also by half, that is 200 volts supply voltage, so that my flux level remains the same. Also, we will also see all the starting methods which we have discussed for the last week. We have discussed different. DOL is anyhow, DOL is no starting method, it's just for a smaller motors. But the other starting methods, the reduced voltage methods, which are reactor method, auto transformer, star delta, what is the purpose of those starting methods, if you remember? What is the purpose of it? The main purpose of those starting methods are just to reduce the inrush current, right? Because whenever there is starting, you have observed they are drawing suddenly high inrush current, and you are seeing the dimness, and your loads are all getting disturbed. So to avoid that, we have gone for the starting methods, and that in the starting methods, what we have done, we are providing our motor with a reduced voltage. Now, reduced voltage, the similar condition we are also experiencing here, if you see, because I am able to have now reduced voltages at the starting only from my power electronic devices. I'm able to get frequency reduced and also voltage reduced here. So I will give this reduced voltage in the starting. So then I will, as the motor picks up, I will shift it. So I don't need any separate uh, starting methods if I have a variable voltage and variable frequency kind of supply. So all your starting methods will also be obsolete if you can able to have this VVVF supply, variable voltage and variable supply. So that's it. Now I can easily change my input voltage and frequency, keeping my these both are having V by F ratio same, so that my flux rated is same, but my operating speed changes. Previously it is 1500 rpm, now it is 750 rpm. I achieved speed control by having a variable voltage and variable frequency. Now the question is, what about torque speed characteristics under this condition? How does the curve look like? Because for the previous condition where we have inserted the resistances and the reduced voltage, you know how the curve is looking like. So this is for resistance insertion, and this is for voltage reduction. This is the curves look like. Now what will be curve look like for this kind of speed control, where you are achieving the speed control below the rated speeds by keeping the V by F constant. So from to actually kind of see how this speed characteristics look like, we need to memorize, like we need to remember the previous 2 weeks before discussion. We got some torque and slips relation from the problems and from derivations we have seen. So we will just write those expression approximately, so that we will be able to relate the relations in that. Okay. Now one relation we remember is torque is equals to K. K is 3V square by 2 pi ns, and is proportional to S alpha by S square plus alpha square. So in that condition, all stator impedances and resistances are all neglected. stator impedances are neglected. Then it will be K. What is the K here? K is equals to, I'll just X2. Now this K, but for if it is T max, you'll have 3V square by 4 pi ns. So that will be there anyhow. K will be gone by half if it is T max. Anyhow, now in denominator, you see of the K, this 3V square by 2 pi ns, you have frequency dependent terms, right, which will decide your torque. Now torque, you have 3 p square 2 pi ns. X2 will also be there in that expression. If you remember, go back to the derivation, you will see the denominator, you will have an x2 and ns. Now ns is already a frequency dependent term, that is 2f by p. Now x2 is also a frequency dependent. It is an omega L, right? Omega L reactance, omega is 2 pi f. There is another f dependent term. Apart from that, everything is constant in this one. We are not varying the supply voltage. Now your maximum torque is now proportional to V1 by F whole square. Okay. Now if you, to keep the V by F constant, you have to vary this voltage and also vary this frequency. And if you are varying this V and F, your maximum voltage is varying to the square of it. If you reduce the frequency and maintain this V by F constant, it looks like T max remains constant, right? Ultimately, you are reducing F, and if you are also reducing V, this ratio is same. Only if you reduce just the frequency, not without changing this input voltage, you can see if you reduce the frequency by half, your maximum torque will go up like 2 square 4 times. But if you keep the ratio constant, V by F is constant, now this T max will be always be constant. That is a importance of it. So this will make you understand, like when we draw the curve for this torque speed, your maximum speed would remain same for different voltages and frequencies. For this condition only we will see the top condition. Now voltage has gone to V by 2 and frequency has gone to F by 2. Now for these two voltages, my speeds, what is the speed? For ns1 you will have 2f by p, and ns2 you will have 2 into f by 2 by p, you will have f by p. So ns2 is exactly half of it. Now if I draw torque speed curve for this is the maximum. Now maximum torque won't change because V by F ratio is constant. And initially, let's say you have a ns1 speed. This is that. This is ns1. Now you have the next speed at ns2 here. Okay, this is your modified torque speed characteristics when you went for a V by F control below the rated speed. Now ns1 and ns2, you have your speed is increasing in this side, and you are able to see how this maximum torque is remain same for a different speed control. You are able to achieve it. Now your T max remains same and your speed has changed. Therefore, for varied frequencies, like there are various frequencies you can operate your motor at, as you F1, F2, F3, you will have NS1, NS2, NS3. Anywhere you can get different speeds by varying different frequencies. But in reality, the stated impedances, everything, they are not that much neglected. They have their own values. So TE max for different values of this will affect a bit. So TE max might not be always constant. Maybe because of the impedances and all, you might see a slight reduction in the T max as frequency falls practically, because there will be extra drop in R1 and X1 as well. So if you draw the exact curve, how it will look like is a bit a reduction in the T max you will observe. This is torque, speed, this is one speed, and this is for it will not have that much maximum speed, but a bit less. This will have that much maximum speed, a bit less, like this. So if you see, there is a reduction in the maximum torque here in this. Instead of same, you will have reduced, but you will have different speeds. This is our NS1, NS2, NS3, NS4. These are for different frequencies. Like there will be operating at F1, F2, F3, F4. But if we see the load requirement, we will have all these speeds at this load requirement. Okay. Now this is what I was saying. So if you are going for a V by F control and reducing the frequency to keep the flux constant, you can achieve a very good speed control under for uh, speed control below rated speeds. The reason why it is only for below rated speeds, because you are reducing the frequency, right? So that you will have to have a, we are seeing, okay, let's say I reduce the frequency, what happens to speed? So when you reduce the frequency, you saw there is a dip in the your flux also. So sorry, increase in the flux also. So to make sure you won't saturate it, you have gone for the V by F control for a lower rated speed control. Now next comes the another question. So can I run my induction machine higher than its rated speed? Speed control. Now I'm talking about the speed control above rated speeds. Can I do that? Yes, of course you can do that. See, you just have to increase the frequency and you will see what happens. So if you want to go above speed, you increase the frequency, reduction, you reduce the frequency. That's what we know. When we reduce it, we saw a problem and we have compensated for the problem by making the VABF. Now let's see what happens if we increase the frequency. Now flux rated proportional to V by F, and I am now increasing the frequency. So if I am increasing the frequency from 50 Hz to 75 Hz, let's say 120 F by P, 4 pole, 30, 75, it will be around some 2000 more than that speed. I am increasing the speed above it. Maybe 55, 60, anything you can, frequency above the rated frequency. Now, if you remember in DC motor, there are two standard speed control techniques in it. It is, if you remember, armature voltage control method and field current control method. So the armature is for below rated speeds and the field current is for above rated speeds. Similarly, you will see a similar kind of behavior for induction machines as well. Now, I can increase the frequency, right? For flux is proportional to V by F. Now I have increased the frequency. What happens to my rated flux requirement? It will decrease. So is there any problem if your rated flux requirement decreases? No, it won't. Your motor will have less rated flux, and then the magnetizing current will also be a reduced magnetizing current you will draw. Now you can't see flux will be reduced. There is no problem of saturation. Now if I am increasing the flux, your voltage should be increased. There won't be any problem of saturation, but there would be another problem. What is that? But you are sacrificing the rated flux. Let's say, okay, I don't want rated flux. Saturation won't be there. So that's a disadvantage. You don't want to go for a reduced rated flux. Okay. Let's say, okay, I want my machine to be at the rated flux. So what I will do, I will try to maintain this V by F constant. So I increased V. I will also increase V. Can you increase V? Input to the windings of the machine. Can you increase the input voltage increment? Like what happens? It is if you increase the voltage, the windings can have this kind of insulation, right? Insulation is provided to avoid any burnings and all. Now, if you increase this voltage above its rated voltage, the voltage is already at rated one. Now, if you increase your voltage above its rated, your insulation might get damaged. So, V by F cannot be constant in this condition where you are keeping your um, frequency increasing. So when you are increasing the frequency, you can't keep V by F constant. Only F would increase, but not V for speed control above rated speeds. So F can increase, V cannot increase, so that your 5 rated will have to go down so that you will operate your machine at reduced fluxes only. So you saw the problem. If you want to have a constant rated flux, it's not possible. So you have to go above the rated voltage and it will damage the insulation. Now, how would the torque speed characteristics look like for this kind of machine where it is above the rated speed? So let's say this one I'm having. Now you know the T max, whatever it is proportional to V by F whole square. Previously in the below, we are trying to maintain this constant, but now it is not constant anymore. Your frequency, if it increases by 2 times, your T max will go down drastically by 4 times, right? Now for the every curve of speed control above rated speed, you have to sacrifice the maximum torque as well, right? This is torque, and let's say you have some curve like this, T max. Now next speed you will have reduced T max. It will be even more drastic. Like this, you will have. See the decrement in the maximum torque you should observe. This is the locus, and and this is, let's say this is rated, and then it is ns1, ns2, ns3, ns4. This is above rated speeds. So the below would be like in the same way, the top curve, and the above would be like this. Now the T max, for every curve there is a T max here, T max here, T max. Drastically it reducing. So another thing is, for every different speeds, you have different fluxes, right? You are keeping the V constant and you are increasing the frequency. You are reducing the flux as well. So it is nothing but similar for the DC machines field current control. There also you are controlling the flux. So it is similar to that of a DC machine. We know. Interestingly, the phenomenon is similar to the speed control of DC machine above the rated speed. Here also above the rated speed, we are controlling the flux. There also flux control is there. So above speeds in both DC and also induction machine, you have to just control the flux. And yeah, now another interesting point here is we discussed many starting methods, right? Uh, Reactor starting, auto transformer starting, data starting. I discussed this point before. Now, but here, if I have this kind of inverter, this is variable voltage and variable frequency, I can also think of starting my machine using this entire setup. So what I will do initially, I won't apply for the full voltage from the inverter. I will supply a very reduced voltage, and I will increase this voltage and frequency slowly. So I'm slowly increasing the voltage and frequency. V by F is slowly increasing. The flux is constant. So my flux rated is also constant, and my machine is also not getting saturated. So I will make sure, and it will make sure the machine doesn't get saturated because V by F is constant, and I will go till rated voltage and rated frequency. So there is no question of inrush currents. There is no question of disturbing the other loads, and but still my machine will be in the rated condition. And again, you don't have to go for any starting methods. So your induction machine starting problems can also be addressed by this VVVF process, that is variable voltage and variable frequency. So these days, we usually see in news that the traction system is developing and people are using induction machine drives instead of DC series motor always. So slowly they are replacing this old DC series motor with the traction system. It started very long back there. They recognize this importance of this variable voltage and variable frequency, and they're replacing it eventually. Now, not only that, the DC series motor also has disadvantages. Previously, since there was no option, we have to go with the DC series motor only. But now, see, DC itself has a biggest disadvantage. What is the disadvantage of a DC? Excuse me. It's the commutator and brushes it's having. So this commutation and brushes, there is already a loss associated with those. They require frequent maintenance and replacements. It's related to very maintenance issue that it has frequent losses in it. So DC itself is a loss, but since there was no option, then we had to go for it. But if not, induction machine is perfect for it because of its rugged construction. It's doesn't doesn't have any maintenance. Once you put the motor to the use, there is no maintenance at all. Very good construction, good performance. If you integrate it with variable voltage and variable frequency, you will get a very good speed control below and above rated speeds. It's easy operation with less losses. So yeah, they're slowly replacing it. Now with these concepts, let's just move to the uh, problem solving session for today. I request to pick up your pen and paper and let's solve for the problems. In these problems, formulas are usually we discussed in the 2 weeks back some relations between this slip, torque and all, we will use those only. It will be very easy and straightforward, but the concepts will be useful. Like if you are inserting the external resistances, how is the torque affecting those? You have to all the have the concepts in mind, and this will be very easy. So let's start solving the problems and see the first problem first. So now we have a question. It's a three-phase wound rotor induction motor. It is having the following parameters: rotor resistance 0.05 per phase, ohms per phase, and rotor reactance is also given. All the losses were negligible. Stator impedance is also negligible. Rotational losses are negligible, and no load current is also negligible. So we are asking to find the maximum torque at slip. So we are asking to find the slip at which the maximum torque occurs. So directly it's alpha, right? Alpha, since the stator impedances all are neglected, 10%, yeah, R2 by X2, that's correct. Since alpha is neglected all the stated impedances, that's right, Dinesh. It is R2 dash by X2 dash. Usually, previously it is R2 dash by under root R2 square, RTH square plus XTH plus X2 dash square. Since XTH and RTH are nothing but stated side, they are neglected, and it is R2 dash by X2 dash. So alpha is equals to R2, which is a resistance 0.05 divided by 0.5. So it's a 10% slip at which your maximum torque will be occurring. It's a very simple problem. The second question is how much resistance per phase you need to add to the rotor to get maximum torque at the starting itself. So we kind of discussed this problem. Like let's say this is your torque speed curve, and this is the starting torque. This is the maximum torque, and this is for the R2. I inserted 0.45. Okay, let's see. I inserted another one. I have got this kind of curve, and I inserted, and I should get maximum torque at the starting itself. So at this condition, this is the starting torque, and this is the maximum as well. So what is that particular thing? Now at the starting itself, so maximum torque means alpha is R2. This is not R2 anymore. It is R2 new. This is some external resistance I have added to it. So R2 new is R2 dash old plus some R external I have added. That will give me X2. X2 is same. Now this alpha will be maximum. So the alpha at which occurs. This is the starting only. At the starting S is equals to 1. So S is equals to 1 now. That's the logic here. When your maximum torque is equal to starting torque, alpha is equals to 1. Now X2, R2, you can find the R external. So R external is equals to X2 minus R2 old. That is 0.5 minus 0.05. That's correct, Dinesh. 0.45 ohms per phase. If you add this much resistance to your rotor resistance, you can get maximum torque at the starting itself. Now let's go to next problem. To get half of the maximum torque at starting, minimum external resistance per phase to be added to the rotor. So this is also similar kind of problem. Previously they said it is maximum, I need maximum torque at the starting itself. But they are saying, okay, I don't want maximum torque, but I want only half of the maximum torque at the starting. So what is the resistance to be added? Now TE divided by TE max at some slip S. So this relation we discussed 2S alpha by S square plus alpha square. Now they are saying that my T max will be twice the starting torque. So T max is equals to twice the starting torque, right? to get half of the maximum torque at the starting. Yeah, so this is twice it. Now, what is the minimum resistance to be added? Now, let's convert 84. Okay, that's good. Dinesh, you are actively participating it, and let's see what I will get also. Now, you just have to convert this into a node relations T max by T start. So I'll just write it. So instead of T, I will write it as T start by T max is equals to 2 times. This is at slip S. At my starting, S is equals to 1. So I will have alpha and 1 plus alpha square. I know this relation, that is 2, right? And T star by T max will be 1 by 2. Okay. Now, you solve this, you will get an quadratic equation. Alpha square minus 4 alpha plus 1 is equals to 0. So if you solve this alpha, you will get some two values. That is one value will have some different value, and you will have to pick up the minimum value from it, which is, I mean, you feel that is valid. So one value will get 0.267. And now if you go with this alpha, you now know the maximum torque, the slip at which the maximum torque occurs. But we already know your alpha is equals to R2 dash by X2. This is R2 new now. So after this condition where you have achieved the twice the starting torque at the maximum, so half the maximum torque at the starting. Now alpha new, that is 0.267 is equals to R2 new, R2 old plus R external divided by X2. Now your R external is equals to 0.267 multiplied by 0.5 minus 0.05. You will get around 83.97 milliohm. That's correct, Dinesh. 84 milliohm. It's simple. From the relation, you need to calculate the slip at which it occurs, and from slip you get the slip maximum torque slip. It's just the formula R2 by X2. Okay. Now the another question. So they are asking that the same question, the addition of extra resistance as in question 3 will make my starting current to be dash percentage. Okay, this is just a relation between currents they are asking for the same condition. For the same condition of this previous problem. Now I need to have a formula for the current here. What is the relation between currents and the resistances? So then it will be easy. So you know I is equals to V by entire total impedance. So the V is constant here. I'm not changing any voltage. It's only dependent on the resistances. Now my resistances have changed, and also here we are neglecting the stator impedances. It's only rotor now. So I new to the I old. So this is what we are asking. So it will be reverse of the ratios, because the new ones will go to the bottom. What is the impedance root of x2 square plus r2 square? At the bottom it will give the old values. Old values is the original 0.05 square R2 and x2 is 0.5 square. What is the new x2? X2 has not changed, 0.5 only. What is the new R2? In this condition previously we have got how much is this we got previously? R2 is question 3. Okay. Total is 0.267. That's the slip now. Total will be this one plus 0.83 plus 0.05. How much is it? 0.05 plus 0.08397. 0.1339. There is a total new resistance now. 0.13397 square. So if you calculate this, how much you'll get into 0.1339 equals to this, the 0.5 under root of it, 0.05 square plus 0.5 square divided by this. So I'm getting 0.97 something. Excuse me. Yeah. So this is, yeah, 97%. So your starting current will make 97% of the original. So you're getting a slight reduction in the this one. Okay. Now let's go for the next question. We have a different set of data for this question. So for a three-phase induction motor with a negligible stator impedances, again we are neglecting all the impedances, rotational losses, and also the no load current. The maximum torque is equals to, okay, we have a typical relation here. T max is equals to 3 times full load torque, 2 times starting torque. This is the relation we have. Now the maximum torque occurs at dash slip. So here also we are asking the relation between alpha is equals to how much. But alpha straight we know R2 by X2. But we don't know any information about R2 and X2. So we can't use that relation anymore. We only know the relation between the torques. So how to calculate it? Right? Any idea? Okay, good. Let's see how we can calculate it. But we know torque, electromagnetic torque at any slip divided by maximum torque, we know the relation is 2s alpha by s square plus alpha square. Now, with this above relation, we can easily get 1 alpha we don't know. If we can know any other slip, we can easily get this. But we know starting torque relation at which s is equals to 1, so that we can have the alpha only, which we can calculate easily. Yeah. Okay. Previous question, right? Yeah, the same problem we have calculated. Yeah, we will get the same equation, alpha square minus 4 alpha plus 1 is equals to 0. That since the relation is twice. Yeah. So alpha is again the same, 0.267. Yeah, good, Dinesh. You could able to understand it's the same problem condition. So again, the slip at which the maximum torque occurs will be 0.267. Now the full load slip is something we haven't calculated, but full load slip you already have the equation. So I will just write with the equation here. T max is equals to 2s alpha by alpha square plus s square. You know the alpha now. You know the if you replace this TEFL TFL, and what is the ratio TFL by TM is 1 by 3. 1 by 3 is equals to 2 SFL into 0.267 by 0.267 square plus SFL square. So now you have a quadratic equation in SFL. So you can solve it, right? SFL square minus 6s into 0.267 plus 0.267 square is equal to 0. So calculate this and solve for the roots and take the irrelevant one. How much? Any idea? It's just calculation only. You can solve it and get the relevant full load slip. Okay, I'm just moving to the next question. Okay, it's okay. There are these are this end of questions. We will solve more questions in the coming week. We will be having one extra session, extra discussion. I will bring more questions to it, and we will solve more questions if we want to. Okay, we got 0.045. Good. Okay, it's good. Okay. We can solve even some more questions on it. We will see. We will have another extra session. We will have a quick revision of the entire syllabus before we close it. Okay, that's all for today. And let's have a quick revision of what we have discussed today. Today we have discussed an important concept of speed control in the induction machines, and we started with the two basic speed controls which we have discussed last week. But we didn't exactly discuss the speed control context, but we have discussed there are two methods by which we can have variation in starting torque as well as maximum torque. One is insertion of external resistance, one is reduction of input voltage. We observed that by doing those two conditions also we are able to achieve the speed control. Both both these voltage reduction and also the resistance insertion. But what is the problem with it? They both have their own problems. Insertion of resistance increases the losses, and reduction in the voltage cannot give you good range, and also reduction in voltage is a very not preferred because it will make the motor stop if it won't meet the load at all. So then we saw the solution for it in introduction of the uh, power electronic devices as a very good solution for it to achieve a smooth speed control. So what all will go into power electronics? It's a AC/DC rectifier, diode bridge rectifier, and we'll have a three-phase inverter. And the pulses to the inverter will be controlled in such a way that we can get the variable voltage and variable frequency as the output, which we will feed to the machine. So we saw the rules and regulations of it, how to decrease the frequency, how to increase the frequency. To achieve below rated, what's the condition? That's making the flux constant, V by F constant. And to achieve the above rated condition, what is the condition? We just don't have to reduce the voltage. So we saw the conditions and we see how the torque speed characteristics, what those curves would look like, and then we solve the problems based on it. Very easy problems, and you also solved with me, and you solved even faster if you know the logic today. That's really good, and yeah, that's all for today. And I would, yeah, if you have any doubts in this today's discussion, you can ask. Okay, if
Yes, sir.
yes, Dinesh.
See, reduction in flux
Yeah,
and reduction in voltage.
yes,
So, like one will increase the speed and one will decrease the speed.
yes,
But magnetic circuit will be unstable in case of reduction in flux.
yes.
So means I want to reduce the flux. I will not reach the saturation. I
Okay,
will avoid the saturation.
yes.
But magnetically the circuit will become unstable.
But now this time you are required rated flux. You are saying.
Yes.
No, no. You have a new rated flux. You mean
1 minute. Just sorry for interruption. Like the machine is designed for a fixed magnetic flux or magnetic field,
hmm,
the slot and all those things, and this area of the magnetic slot and core.
yes.
So reduction in flux, like magnetically, the circuit is not stable. The design value.
You mean the motor will not be put used to its capability. We can't use it to its capability.
Yes, like torque will reduce significantly.
That's the disadvantage we have seen. So your motor will not be stable. Like not stable means it will work, but it will very poor condition. You can't have good torque profile, you can't have good flux also. But yeah, your speed control you can achieve it. That's the downside of controlling speed above rated speeds. You have to increase the frequency and your flux will go down, and your core won't be magnetized good. You won't be able to use the machine because you know your machine is capable of giving that maximum torque, but you are never going to use it, right? Is that it? Okay.
Yes, sir.
Okay. Thank you. So yeah, that's all we discussed, and some problems. If there are no doubts, we will meet you next week. Thank you for listening.
Further problems can be solved, sir. Like after
Sorry,
6 and there are
further
many more
problems.
problems.
Yeah, there are many more problems. Tomorrow you have a session, right? Tomorrow you don't have a session, so
No.
I can solve two more problems. Okay, let me just bring out the questions for it and look into it. Just give me a couple of minutes. I'll just bring up the questions. So I'm sharing my screen. We can solve two more problems. If we want to discuss more problems, I will find some time. So yeah, so we were asked to estimate the required percentage reduction in the rotor resistance to bring down the full load slip to 3%. Now we were given some new full load slip, and we need to have a ratio between the rotor resistance. Now we know the old values of rotor resistances, and we need to calculate the new per, percentage of rotor resistances to get the reduction in the voltage. Now we know alpha alpha which is at the maximum torque occurs. Alpha is equals to R2 by X2. Now if you can calculate the percentage reduction in the slip, it is nothing but the percentage reduction in the R2. Now we need to have a relation between the full load slip and the alpha. If you know, see now you know this full load slip right now. If you can able to get the relation between these two, how much your alpha is changing, then you can get the percentage reduction in the R2 as well. So what I'm saying is you were given a new full load slip, that is 3%. From the previous problem, you have the this relation, right? This SFL square 6s alpha. This is alpha plus alpha square. This is what we have a relation. Now you will have a new relation now. For this condition, alpha old is 0.267. Alpha old 0.267. Now if you can get alpha new, then you can have percentage reduction between these two, alpha old and alpha new. So your aim is to calculate alpha new now. So you calculate SFL new, this is this one, SFL square minus 6 SFL into alpha mu plus alpha mu square. is equals to 0. So in this you know SFL, that is 3%. Now substitute SFL is equals to 3 and calculate the alpha nu here. 0.003 square minus 6 into 0.03 alpha nu plus alpha nu square. You calculate the alpha nu from alpha old, you already know the R2. You can get R2 old and R2 new also, and you can get the alpha new alpha old ratio as well. Now if you calculate alpha new, you would get 0.1749. So this alpha new you would get. Now you know alpha new and alpha old. You want to calculate the percentage reduction in the rotor resistance, which is also analogous to percentage reduction in the alpha nu. So from 0.2672 your nu alpha is reduced 0.1749. Now the percentage reduction would be alpha whatever old minus nu divided by old multiplied by 100. That is the reduction. So calculated 0.267 minus 0.174.267. It will be 267 minus 0.174 divided by 0.267. 0.34% around. Yeah, 34.8%, you can write it. 34.8% reduction got when you have brought down your full load slip to 3%. So that's it, and let's solve another problem. Now after the rotor is redesigned with the reduced resistance, yes,
So like there is a 2 L S full load.
huh,
The ratio of the S old full load to T max will be equal to the SFL new to T max.
I didn't understand. T
There is a
max,
ratio of T full load to T max. We are taking it as a 1 by 3.
okay, right.
So to the new sleep it will be the same.
No, no, no. Slip won't be same because for the changed slips, your 2s alpha by alpha square plus s square, this entire product will change. You are not just taking they are not proportional. There is a 2s alpha by alpha square plus s square. If you see the value of it, they will change. There won't be 1 by 3 anymore. 1 by 3 is only at old values, but for new values, you can directly check now itself. For the S new and alpha, if you calculate the ratio, only 1 by 3. That
Okay,
won't.
okay, okay.
Okay. Another problem is after the rotor is redesigned with reduced resistance, as in question 7. So previous, okay. Now we know the resistances. Let's say we are redesigning it with the rotor, and starting torque will become dash percentage. Okay, we were asking the ratios of old previous. Okay, new to the old. So T starting torque divided by T old dash percentage. Okay. Now they are not asking percentage reduction, but torque is how much percentage of old. So that is just a ratio of both they were asking. Now to get a ratio of starting torques, you need to calculate first the ratios first. Now that's what you just asked, right? The ratio won't be same because previously we have a starting to the max 1/2, I guess. Now what what will be the new ratio now? So I will write old here. T starting old by T max old is equals to 1/2. So we know this. This is 0.5. Let's say this is equation 1. Now with the redesign value, we will see ratio T starting new to the T max nu. Starting anyhow, the slip will be 1 only. Now alpha nu will be there. Yeah. 1 plus alpha nu. So as in question 7, what is the alpha nu? 0.1749. So 2 times 0.1749 divided by 1 plus 0.1749 square. So you calculate this around how much it is? 2 into 0.1749, 0.1749 to 0.1749 plus 1. So you will get 0.339 something I'm getting. So this is one equation, one ratio you have and another ratio you have. You can just get the ratio. Now get the ratio of it. Okay. Now one concept you have to remember, like here they are reducing the resistance. So for the reduced resistance, like this you will get, another you will get, and another you will get. So for this reduced resistance, what remains same? Maximum torque remains same. That means your T max new and T max old is same. If you take the ratio of it, they both get cancelled. That's what I am trying to put it. So you need TST new divided by T max new divided by TST old divided by T new old. Now T max and T max old and new get cancelled because whenever you are varying the resistances, your maximum torque remains same. Again, you have to remember this concept that you again that should strike your thinking. Now, what is the numerator? New one is 0.339 and the denominator is zero point 0.5. So this will give you the percentage of new to the old. 0.339 divided by zero point 0.5. 67.8. So your new torque would be 67.8% times of the old old starting torque. These are the key concept you have to remember. So it's okay. It's almost 8 o'clock. If there are more problems, we will find another extra class and we will solve more. We will discuss more problems and all. That's not a problem. But okay. So yeah, if you have any doubts in this new two problems, you can ask. I hope they are clear. You just have to get the idea like how can we solve quickly. Like they are asking about ratio of old and new talks and how I can get it and what is the relation between those two and what's the relation between maximum talks when rotor distance is changing. Everything you should be at fingertips. And yeah, okay. Yeah, 68%. That's correct. Okay, that's all for today. Thank you, Dinesh. Thank you for actively interacting and solving the problems with me. And I also make sure you are also understanding it and you're also listening to it. So yeah, let's meet next week and we will discuss more concepts and see you next week. Thank you.